Good evening, everyone. Welcome to the third session of Space Tech webinar series, organized by Satellite and IT Division of SEDS, Sri Lanka Technology Campus. We are absolutely thrilled to have you join us today as we continue this exciting series exploring space and its technologies. I'm Tarindu Pahasara, representing the Comparing Committee of Media Unit of Sri Lanka Technology Campus. To officially welcome you all, I would like to invite our project chairperson, Dilusha Chamod, to deliver the welcome speech. Dilusha, over to you.
Good evening, everyone. It is my great pleasure to warmly welcome you all to the Space Tech 2026, the official webinar series organized by the Satellite and IT Division of SEDS SLTC. On behalf of the organizing committee, I would like to sincerely thank each of you for joining us today. Your presence reflects your interest and enthusiasm for space science and exploration. We are especially honored to have Mr. Lahiru Udara with us today. He will be leading this session and sharing his valuable insights on foundation of rocketry and space travel. I encourage everyone to stay engaged, listen carefully, and make the most of this wonderful opportunity to learn. Once again, a warmly welcome to the Space Tech 2026. Thank you.
Thank you, Dilusha, for those inspiring words. Now, it's my absolute honor to introduce our esteemed guest speaker for today's session. Joining us today, Mr. Lahiru Udara, an operation engineer at Robotic Assistant Devices. He holds a Bachelor of Honors in Mechanical Engineering, specializing in Mechatronics from the University of Moratuwa. And he also the former president of SEDS, University of Moratuwa. We're delighted to have him with us today to share his valuable knowledge and experience. So, Mr. Lahiru Udara, the virtual stage is yours.
Good evening, everyone. I hope you guys can hear me properly.
Yes, sir.
Okay, thank you. So, first of all, I would like to thank SETS SLTC for inviting me to this wonderful session. I always encourage everyone to learn all the time. So this webinar series is a really good thing for everyone who wants to learn about space, rockets, and everything related to space. So today, today our session is about the foundations of rocketry and the future of space travel. So in this session, I'm going to talk about two main aspects. One thing is the basics of the rockets and rocket engines, rocket propulsion, and everything. And then the next part is the future of space travel. Let's start now. So starting with the rocket. So what do we call a rocket? Rocket is basically any vehicle with a rocket engine. So basically there are four main parts in a rocket. So the first thing is the structure system. Structure means everything that holds the rocket together. So basically from the nose cone to the fins, everything in between is the structure of the rocket. Then we have the propulsion system. Propulsion means basically rocket engines and the propellants, fuel, oxidizer, and everything. Then we have the guidance system, which is the computers, electronics, electrical systems, basically the brain and the nervous system of the rocket, which helps to control and guide the rocket on its path. Hence the name guidance. Then finally, the payload system. So a rocket, or the correct term here is the launch vehicle, is used to send a spacecraft to basically into space, but it could go anywhere. Like it could be low Earth orbit, medium Earth orbit, geostationary orbit, or maybe the moon, Mars, Jupiter, anywhere. So the payload is what the rocket takes with it. So rocket's job is to send the payloads on its way. So the payload system comes with the attachment system, which connect the spacecraft to the rocket, and the electrical wirings and all the other connections up until it is separated from the rocket to start its journey towards its target. So let's start with the structure. So structure of a rocket basically consists mostly with the tanks. So tanks, we all know about tanks, but when it comes to rockets, tanks are kind of different. Usually, a rocket stage has two propellant tanks. One contains the fuel and other contains the oxidizer. So in here, in this image, we have the second stage of the Saturn V moon rocket. This large tank is for liquid hydrogen and the small tank is for liquid oxygen. You might wonder why we have like two different sizes for the tank. That's because of the density of each propellant. You know, the hydrogen has a very low density, so it has a large tank, and oxygen has a much higher density, so it has a smaller tanks. So each tank is consist with multiple components. So this large tank, it has a dome, then it has multiple cylindrical section. Everything is welded together. Then we have the oxygen tank. It also consists with domes. And the bottom of the structure, we have the thrust structure. So this part is very valuable because rocket engines are attached to this thrust structure. So all the forces, the thrust coming from rocket engine is acted on this thrust structure. And this is very important because this one has to endure all the forces it's getting from the engines, and it has to distribute this force to the tank wall, because in a rocket, this wall of the tank is the structure. There is no other structural elements holding the tank together. It's the tank itself. So thrust structure gets all the thrust from the engines and distribute it towards the circumference, the cylindrical portion of the tank. So that's how the whole rocket moves together. So this part is very important, the thrust structure. Then we have the forward skirt connecting to the third stage, and we have the aft interstage which connect to the first stage. So this is the second stage. It sits between the first stage and the third stage. When it comes to tanks, there are two main types of tanks. So the first one is, it's called the structurally stabilized tanks. This means the structure of the rocket is strong enough to hold the entire tank. You might wonder, like, if the tank cannot hold itself together, it would like collapse on itself, right? Yeah, it happens. That's why it is structurally stabilized. This means the the inner side of the tank is made in a way to increase its strength. For example, this rocket stage has this, the square, rectangular shaped components cut out from the skin. So it has this orthogrid structure. This is called the orthogrid. And that gives the strength for the tank. Because the other type is called the pressure stabilized tank, which means the structure of the tank is not strong enough to hold the tank together. So that means if these tanks are not pressurized, this will collapse. So I have a video. So this is the Centaur rocket stage. It's been used. I think it's been used since 1960s until today, and it will be used far into the future, I guess. So this is a very old rocket, but in this video, you will see what I just told you. So this is the Atlas rocket, and it also has pressure stabilized tanks, which means accidentally, if it lose pressure, it would collapse. So you can see in here, accidentally, the pressure gets released from the tank. So just rocket just collapse on itself. So you can see. So yeah, that's what happens if you lose the internal pressure on a pressure stabilized tanks. So if these tanks are that weak, if it cannot hold itself together without pressure, why would someone use these weak tanks for a rocket? Right? That's a valid question. Like, why would you need a very weak rocket tanks? The thing is, the job of a rocket is to send something into the space, orbit, or wherever the payload is going. So in order to maximize your payload capacity, you need to make sure that your rocket is as the weight efficiency of the rocket should be very higher. That means the structural weight of the rocket should be as lower as possible. So if you are a rocket engineer, your job is to basically reduce the weight as much as you can. So one of the clever trick is this. You just take a very thin sheet of metal and make a tank out of that sheet. So this is basically sheet metal tank. It's very thin. So it doesn't have the enough strength to hold itself together. So you need to pressurize it to like make it like a balloon. So these are called balloon tanks because if you like pump air into a balloon, it can lift something up. But if you remove the pressure, it just collapses on itself. So both of these tanks are used on rockets. Then tank pressurization. So the pressurization is crucial for pressure stabilized tank, but for a structurally stabilized tanks, it also needs tank pressurization. That is because now before the launch, the rocket tanks are basically filled with propellants. But as you go up, the level of propellants reduces. So that means initially you had higher pressure for the engines, like the liquid pressure proportional to the height of the liquid. So when the tank is full, you have a lot of pressure at the bottom of the tank, which means you have a high inlet pressure for the rocket engine. But as the level of the propellant goes down, the pressure here reduces. That is not good because you need to maintain a constant pressure for the rocket engine inlet. So to keep up with the loss of propellant, you need to increase the pressure above the liquid. So that means you take a gas like helium, which is, is non-reactive. So you pump helium to the top of the tank as the propellant level goes down. So in that way, you can keep almost constant pressure near the engine inlet. Now, one trick is to basically use helium to pressurize tank. But to do that, you need extra set of tanks to store helium. I said like job of the rocket engineers basically to remove mass, remove weight as much as possible. So if we want to remove that helium tanks, what do we do? We can use the propellant itself to pressurize the tank. So what you do is, this is the Raptor engine from SpaceX. So it takes liquid methane, CH4 is for methane. So you take liquid methane and liquid oxygen into the tank, into the rocket engine from tanks. Then you, a small part of that propellant is vaporized and it is pumped back into the tanks. So you take liquid, heat it up a little bit, then send a small percentage as a gas to the tank. So in that way, you can basically remove helium or a third pressurization gas. So this is called autogenous pressurization. So this is used on Raptor engines, so which means it's used on a Starship. Then we had this system on the space shuttle. So this old system. And imagine the rocket is going to the space. First stage engine was shut down. It was removed. Now the second stage engine, it's time to ignite the second stage. But now you are floating in the space. So the liquid just float inside the tank. Now you cannot start the engine because you don't have liquid at the inlet of the rocket engine. If you start it like that way, you are not getting liquid into the tank. So your pumps rotate at a much higher speed and it will just explode. So this is not good. You need to get these liquid bubbles back into the bottom of the tank. So how do you do that? So you need small rocket engines, which calls ullage thrusters. So this process is known as ullage. So ullage thrusters, basically a small rocket engine just fires, giving a small acceleration. So it will just push those liquid bubbles back into the bottom of the tank. So now you can start the rocket engine. So if you watch a rocket launch, let's say SpaceX Falcon 9 launch, you can clearly see these ullage thrusters are fired just before the ignition of the second stage. So you can watch a video on YouTube and you will see that. Okay. Now, multi-stage rocket. Modern rockets have multiple stages. The reason is for that because you can just remove weight as you go up, so it will be much efficient. Otherwise, if you are doing a single stage rocket from the ground to all the way to the orbit, it has to be a very big rocket. But you can do a multi-stage rocket and carry that same payload in a much smaller rocket. So this is weight efficient method. So this is a Delta II rocket. It has the first stage and 9 rocket boosters, then the second stage and the third stage and the payload, which is here is the Kepler Space Telescope. So now we are going to talk about how a rocket is manufactured. So we are diving into a rocket manufacturing facility. So everything starts with metal sheets. So these are aluminum sheets. Most of the rockets are made out of aluminum alloys. The main reason is aluminum is very lightweight and it has good strength relative to its weight. So, but you cannot take this bulky metal sheet for the rocket. you need to cut down some weight. So to do that, what you do is you take a milling machine and you start to cut the different shapes. You can do different shape. Earlier we saw a rocket it has rectangular cuts, so it was called orthogrid. Here you can see triangular cuts. So the center, these parts are milled away. So this is called a milling machine. So it's just basically kind of a drilling machine, but the purpose is not to drill a hole, but it just move around, removing the material. So doing that, by doing this, you can reduce your weight by a large margin while keeping most of its strength. So that's why most of the rockets have this kind of a milling pattern. So this is called the isogrid. The previous rectangular blocks are called the orthogrids. So these two patterns are used when manufacturing a rocket tank. Then we have this. So you can see milling part is done. Next thing is you need to bend this long sheet into a curve, because you need to attach multiple curved sheets to make a cylinder. So these are the welded lines. So most in modern day rocket manufacturers use friction stir welding to weld these parts to make a basically barrel. These are called barrels. And to get the appropriate height, you can attach multiple cylinder barrels to get the appropriate height of the rocket stage. If you want to watch this whole video, so this is a screenshot I got from the video. It's from the YouTube channel called Smart Everyday, from this guy, Destin. So he's inside the rocket factory of United Launch Alliance. So he's the former CEO and he's the Destin. So you can go check out the channel Smarter Everyday and you can see the whole factory tour. So here we have two completed tanks. Then you have to attach these two tanks to make the whole stage. After that, you need to attach rocket engines, electrical wirings, computers, and all these other components. And then you have to send these to the launch pad, because most of the time rockets are not manufactured near the launch pad. There are multiple reasons for that, but for transporting, we have multiple methods. So one of the method is you can use a big ship and use the ocean or any waterway to transport these big rocket stages. The reason is there are limitations for the size for road transportation. For example, this is a Falcon 9 first stage. You can see SpaceX logo here. So Falcon 9 has a diameter of 3.8 meters. The reason for that is the maximum size for anything that is allowed to transport through roads in America. So Falcon 9 was manufactured keeping that idea in their mind. So we don't need big ships or aircrafts to transport our rockets. So in order to transport these on the main roads, we need to limit the size of the rocket to 3.8 meters. So that is the diameter of the Falcon 9 rocket. But the Delta IV rocket has a 5-meter diameter, so it cannot be transported on the road. This Atlas V first stage. Another method is to use an aircraft to send these. And this Vulcan rocket first stage, it's also those are also transported through this rocket ship of the United Launch Alliance company. So once all the stages are delivered to the launch pad, next thing is called the integration. So there are two methods. One is the horizontal integration, the other one is the vertical integration. These things like explain themselves. So horizontal integration means you are assembling the rocket in a horizontal way, and the vertical integration means you are assembling the rocket in a vertical way. So that's basically it. So this is the Falcon integration facility. So you can see 4 first stages here, and this one has been integrated with the second stage and the Dragon spacecraft onto the launch platform. Here you can see the launch platform. And here ULA, United Launch Alliance Company, used vertical integration. So first stage is, you can see it's been transported onto the launch platform here. Then the second stage is hoisted and placed on top of that. Then the payload. So one of the main reason is some payloads cannot be integrated horizontally. Like you can have like a very delicate thing like a space telescope, let's say. So if you are using horizontal integration, you have to transport it to the launch pad in a horizontal way. Then you have to raise it up, turn it 90 degrees. So some delicate instrument on a space telescope might not be designed to withstand that. So in these cases, vertical integration is the best. So that's why 2 companies use 2 different methods. Once the integration is done, then we have the rollout. That means taking the rocket into the launch pad, and rest is the launch. So another thing I need to mention about tanks is the insulation of the tank. So most rockets use cryogenic propellants. That means these liquids are gases in room temperature. For example, liquid oxygen is used as a oxidizer, but it's a gas. Oxygen is a gas at room temperature. So you need to cool it down to minus 183 degrees of Celsius to make it a liquid. But once you fill that cold liquid into a tank, the outside of the rocket is, the normal environment. The heat will just come into the tank and it will start to again vaporize those liquid. So to prevent that, you need to add a thermal insulation around the rocket tanks. Still, we don't have perfect insulators in the world. So you can see, for example, this Electron rocket. This is before the propellants are filled into the rocket, and here we have a completely full rocket. You can see this part is covered with ice. That's because this part has the liquid oxygen, so it's very cold. The water vapor in the atmosphere just cools down and become ice and deposit on the outside of the tank. So you can see this is the liquid oxygen tank. This part is still the black. This is a carbon fiber rocket. This part still remains the black because that's the fuel tank. That's the kerosene. So it's a liquid at the room temperature. So it's not cold. So on the second stage, it's the same case. This is the fuel tank, kerosene, and this is the liquid oxygen tank. So you can see the layer of ice on the outside of the tank. So that's the structure and the structure, tanks, and everything about rocket in a basic way. Then comes to the hard part, the rocket engines. So here I have like a small mathematical part here. The thrust of the rocket engine is measured basically. The Newton's equation F equals ma. So this is a different version of it. So this is the m dot v type. So that means this is the mass flow rate. That means how much mass you are shooting out of the rocket engine. So this comes as kilograms per second. Then the VE means exhaust velocity. That means what is the speed of this mass. So let's say we are expelling 1,000 kilograms per second out of the rocket engines at a speed of 1,000 meters per second. So you have to multiply those to get the thrust of the rocket engine, and we have a small part to add, that's the pressure part. The pressure difference you get from the area of the rocket engine, but that's mostly we can neglect that this point for simplification. So F equals m dot v. So when it comes to rocket engines, we have two key metrics. One is the thrust of the rocket engine. The other one is the efficiency of the rocket engine. So in normal vehicles, we use kilometers per liter. Like, okay, for a bus, it's like 5 kilometers per liter. For a car, it could be 20 kilometers per liter. But when it comes to rocket engines, we have to use a kind of a different metrics to measure its efficiency. So it is called specific impulse. Impulse means a force multiplied by the time. Then when it comes to the specific, that means you are dividing it by the mass flow rate or the mass. So we can rearrange this one using the m dot v, and m dot means m is divided by t, and you get ISP, or the specific impulse, is equal to the exhaust velocity. That means, in a simple term, the higher the exhaust velocity of a rocket engine, the efficiency is better. So that's basically it. Like, you need okay. So these two things are the key metrics of a rocket engine. So if we have a higher exhaust velocity, that means the efficiency is much higher on that rocket. And one other thing I need to mention, you might have heard when you are watching like a rocket launch, maximum dynamic pressure, or max Q. So that basically means the force acting on the rocket as you are going through the atmosphere. So this is decided by two factors. One is the rho, or the density of the atmosphere, and the velocity of the rocket. Now here's the interesting part. At the launch, your velocity is 0. So dynamic pressure is 0 because this part is 0. In space, there's no atmosphere, so atmospheric density is 0. So here it's also 0. Now what happens? So when you are launching a rocket, the velocity increase, but the atmospheric density goes down. So here we have the multiplication of the rho and v square. So at one point, you get the maximum dynamic pressure acting upon the rocket from the atmosphere. After that part, at that moment, even though your velocity increase, the density of the atmosphere goes down. So the result of this equation is smaller than this maximum dynamic pressure point. So that's why when launching a rocket, it matters. You can hear they call max Q, or maximum dynamic pressure, when the rocket reach that maximum dynamic pressure, which is a critical point for the structural integrity of the rocket. Okay, now around the world we have a lot of rocket engines, and these rocket engines use different propellants. Some use kerosene, some use hydrogen, some use solid propellants. Starship use liquid methane, or there are all sort of propellants. Is there any like the best rocket propellant in the world? The thing is, there isn't a one rocket propellant that is like superior to everything. For example, let's say F1 engine on the Saturn V rocket, it used RP1, means refined petroleum. So refined petroleum and liquid oxygen. The specific impulse was 263 seconds. And if you take the Raptor engines, which use liquid methane and liquid oxygen, you have 327 seconds. But if you take RS-25, which is the space shuttle main engines, it has 366 seconds. So it's much higher than the Raptor engine. So why doesn't SpaceX use liquid hydrogen as their propellant? The reason is they are aiming for the Mars. So they want to send Starship to Mars, and you can make methane on Mars very easily using carbon dioxide on the in the atmosphere and the water ice. You can also make hydrogen on Mars, but hydrogen has a much lower density, so you need to have very big tanks to hold it. So when you are designing a rocket, you have to consider a lot of things. Economy and the target of the rocket, where you are sending this rocket, and cost, then the manufacturing, like the propellant production, storage, and all these factors, and also the thrust. So for the rocket engine, F1 engine is still the most powerful rocket engine with a single combustion chamber. So it has 6.7 meganewtons. So that's millions of newtons of thrust. But the RS-25 only has 1.10 meganewton. Raptor is around 2.5, I guess. Now these are like old Raptor version. So different rocket engines use different propellant. The choice is based on multiple reasons, and the thrust levels are also different. Like you have to make sure your rocket engines is the best suited for your application. So that's why there's no ultimate superior propellant in the world, or ultimate like superior rocket engine in the world. Everything is different, and those are made for different purposes. Then another basic things, liquid rocket propellants versus solid rocket propellants. So if you're using liquid rocket propellants, your rocket engine could be shut down and restarted because it's liquid, and you can throttle the engine, like you can change the thrust, and liquids tend to have a higher specific impulse. But a liquid rocket engine is much more complex. It has valves, turbine, pumps, and etc. And most of the rocket propellants we have that are not toxic are cryogenics. For example, liquid hydrogen, liquid oxygen, liquid methane. These are like cryogenic propellants, which means you have to cool those down. There are some storable propellants, that means liquids at room temperature, but those are really toxic. For example, monomethyl hydrazine, dinitrogen tetroxide, both of them are liquid at room temperature, but those are much toxic. It's not good for the people. And also liquid have a lower density compared to solids. Of course, like liquid has a lower density compared to solid. But solid rocket, these are simple, cheaper to manufacture. Propellants are solid, so it's storable. You can like store the rocket with propellants filled inside. And since it's solid, propellants have higher density. But once it's ignited, it cannot be shut down. That's the one of the like a major drawback of a solid rocket. And also you cannot throttle it in real time and have a lower specific impulse. So you can see like even the liquid and solids have pros and cons. So you have to choose what you want. So you cannot say liquid are the best or the solid are the best. Each of those have good side and the bad side. Yeah, so then there are some other stuff. So usually when we talk about rocket propellant, we talk fuel and oxidizer. You have two components. Those are called bipropellants. And there are some other propellants called monopropellants. That means you don't have fuel and oxidizer. It's just a same one liquid. So since there are no oxidizer here, there's no combustion. What you do with hydrogen peroxide and hydrogen is you basically decompose it into like gases. So you take hydrogen peroxide and you can decompose it into oxygen and water vapor. So it's kind of a rocket engine, but it is less efficient compared to a bipropellant rocket engine, which has burning or the combustion inside the rocket engine. Another thing I want to like quickly mention here, in A-level chemistry class, you should have learned about stoichiometric ratio. That means like the correct ratio of in a chemical reaction. For example, if you take hydrogen and oxygen, you can make water, but in order to balance the equation, you need two hydrogens with oxygen to make two hydrogen atoms. So hydrogen I'm sorry, I had like internet connection issue for a moment. You guys can hear me, right? Again. Okay. So I was saying, if you have more fuel in the combustion, you have leftover fuel in the combustion. So these are called fuel-rich combustion. Then if you have more oxidizer in the combustion, you have remaining leftover oxygen after the combustion. So these are called the oxidizer-rich combustion. So the reason why I am telling you this, because when it comes to rocket engine, rocket specific impulse, the efficiency change according to the combustion ratio. For example, if we are this is basically the specific impulse. So you can see at a specific mixture ratio, you get the highest exhaust specific impulse. So that is where all the propellants are burned in the stoichiometric ratio. So if you have more fuel or more oxygen, your specific impulse is low. So for example, for a liquid hydrogen, liquid oxygen combustion, the proper mixture ratio is around 5.5, between 5 and 6. Then for the kerosene, you have 2 point something, and the methane also you have 3 point something. So we have different mixture ratios but the thing is, like, you might think, okay, we need to get as much as specific impulse out of the rocket engine, right? Yes, theoretically, yes, we need to get as much as energy, as much as specific impulse from rocket engine. But there are some practical limitations. The one thing is, if you are burning at the best energy efficient ratio, the combustion temperature is at the highest value. So this is the hottest combustion, the highest temperature. So your engine might not survive that temperature. So you need to cool down the combustion a little bit. So you can go toward a little fuel rich combustion or oxidizer rich. So that's why I said, like, there are some practical limitations and practical reasons not to use this optimum best combustion ratio. So most hydrogen oxygen rocket engine, you are burning around 6. The mixture ratio is around 6. So that is not the optimum value. It is little bit off balance, but it has a cooler combustion in the combustion chamber. So that's the difference between the theory and the real world application. Okay. One of the most complex thing in a rocket is the injector. So injector is basically how you mix a liquid fuel and the fuel and the oxidizer in the combustion chamber. You might think, oh, it's very simple. Like, you have one hole for the fuel, then you have one hole for the oxygen, and it just combust. That's it. It doesn't work like that. For example, so this is the injector plate of the F1 rocket engine. You can see there are a lot of holes, and you can see these holes are like angled in a way two streams will hit each other, That's why it's inclined, angled. So these are not straight holes into the plate. All of these are inclined holes. So there are thousands of holes in this injector plate at a very specific angle. And the other thing is, one set of holes have fuel and the other set of holes have oxygen. So the backside of the injector plate is very complex to get one set of holes to have oxidizer and the one set of holes to have the propellant. So this is like the simplest way of an injector. So you have two fuel is coming at angle and you are injecting the oxidizer straight, so everything will hit at one point and it will just mixed. So without this without a proper mixing, you cannot get the good combustion. So here you can see how these are made. So we have these big holes are like center holes and the other two are inclined holes. So those are called triplets because it has 3 holes. Now we have quadrets, so you have 4 holes, 2 shooting fuel and 2 shooting the oxidizer. Then we have the other one, the fuel injector. That means you have a kind of a small cylinder, and the bottom of the cylinder you have 2 streams, but they are entering the cylinder at offset position. So these will like make a rotating effect, and once it reach the top, it will just spray out. So it's a very efficient way. In the same way, you can have 2 central cylinder and an annular hole. So these are called coaxial fuel injectors. So all of these are used to make a proper mixture. Like, without a good mixing of the fuel and the oxidizer, you cannot have a good combustion. And this is a very simple one. It's called the pintle injector. So everything I said before, those have a lot of holes on the injector plate, like thousands or maybe 100 or thousands. But pintle injector is a simple one injector. So here you can see how it works. Like I don't have to explain. So these will inject at an angle and these will inject at a different angle. So it will hit somewhere. So this is a real spindle injector. So here you can see these propellants. This is a water actually. So this is a testing. So these liquids are shooted out like in a radial way, and we have another one shooting the other propellant in the axial way, and both of them collide and cause a really good mixture. So this spindle injector only has one injector compared to the triplets, quadruplets, and the coaxial swivel injectors and everything. So this is like kind of a simple way. These are used on Merlin engines on Falcon 9 rocket. Okay. So the reason why I explained about injector is the injector technology is considered as kind of a secret of a company, because the performance of the rocket depends on the injector. If you don't get a proper mixture, you don't get a proper combustion. So if you like search injector plates on rocket engines in America, you cannot get the current version of the injector plate. These are considered as secrets. So you can see like old injector plates, like I showed you the F1 engine from Saturn V, but you cannot get a clear image of a modern injector plate because it's a secret for like almost all rocket companies, because it is a very crucial part of a rocket engine. Okay, I have a question for everyone. Can anyone identify this rocket engine? Like, does anyone know the name of this rocket engine? This is kind of like a popular rocket engine, actually. So if you know this, you can just type in the chat, say the name of this rocket engine. Okay, it seems that okay, it seems that you guys don't know what this rocket engine is. So this is RS-25, or it's called the Space Shuttle main engines. And currently these rocket engines are used on the SLS rocket, not Sri Lankan standard, the space launch system, the rocket that sent 4 humans to moon in April. So this engine is one of the most complex rocket engine in the world, and due to its complexity, it has one of the highest specific impulse you can get from rocket engine. So this is like a really good, efficient rocket engine. So now I'm going to like do kind of a deep dive into this rocket engine. So by doing that, I think you all can like learn components of rocket engines. Like there are so many types, but this is like one of the most complex one. So you can get an idea about the parts and how a rocket engine works in real life. So this is very complex. I get it. Like, so here we have temperature and the pressure and the flow rate at each point of the rocket engine. So these are in Fahrenheit, PSI, and pounds per seconds, because I got these from America. You know, Americans use these units still. So this American engine, so that's all we have. But I know this is very complex. Like let's take a simple look. So here's the main structure of the rocket engine. You can see the nozzle, we have the combustion chamber, we have 2 turbines. Yeah, there are turbines in rocket engines. So let's move forward. First, we add a pump. So this is a pump. So this is the low pressure fuel pump. The reason we call this low pressure because this will increase the pressure of the fuels in a low, like kind of a low value. So you can see we have inlet pressure from the tank is 30 psi, outlet is almost 300 psi. So it has increased the pressure by 10 times. And you can see the RPM of the pump, it's 15,000, 15.5 thousand basically. Then that fuel comes to the high pressure fuel pump. So this is the low pressure fuel pump, this is the high pressure fuel pump. Here we get to a pressure of 6,000 psi. So you get from 300 to 6,000. So that is like 20 times. So fuel is injected, like fuel enters the engine at 30 psi. Now you have 6,000 psi. So it's like really high pressure. Then what do you do? So this is RS-25 engine. So this is liquid hydrogen. It's very cold. You can see it's minus, so 367 degrees of Fahrenheit. So we can use these to basically cool the combustion chamber, because when the rocket is working, we have combustion happening here and the hot gas coming out from the nozzle. So everything here is very hot. It's like at thousands of degrees of Fahrenheit. So we need to cool that, otherwise it would melt. So we are basically pumping this high pressure cold liquid hydrogen through the basically there are some channels, there are some path made inside the nozzle and the combustion chamber. So this cold propellant flows through the walls of this nozzle and the combustion chamber. So it cools down the engine basically. After the cooling, you can see as it absorbs the heat, the temperature has risen to minus 193 degrees of Fahrenheit. So now we get this relatively warm liquid, and we divide the channel to two sides. One is to the fuel side and the other goes to the oxidizer side. And another small part of this propellant is used to drive the turbine here, because I said this is a pump, and pump cannot work like automatically. You need to rotate the pump. To rotate the pump, you use a turbine. So this is a pump, this is a turbine. When the hydrogen flows through the turbine, it rotates and it will rotate the pump. So that's how the pump works. So now you might wonder, okay, how does this pump work? There are turbines, we will get there. So a small part of the propellant is used to pump the low pressure fuel pump. And that fuel is injected to here and here. Okay, fuel side is done. Now let's move on to the oxidizer side. As the fuel side, we have low pressure oxidizer pump. So we have 100 psi, that's the inlet pressure. It is increased to 421 psi, and it's very cold, liquid oxygen. Then it goes to the high pressure oxidizer pump. So it's now 4,000 psi. Then what? Then we just pump most of the oxidizer into the main combustion chamber. And the small part of this high pressure oxygen is used to rotate the low pressure oxidizer pump. That's how the low pressure pump works. And we take a small portion of the oxygen and we use another set of pump here. It's a very small pump because we are taking a small part. So for example, we are taking basically 1000 pounds per second of liquid oxygen, and 839 pounds of that propellant is injected into the combustion chamber, and the rest is and some part goes to here to rotate the pump, and the remaining 92 pounds per second flow is directed to this small boost pump and increase the pressure to 6939 psi. And these are injected to here and here. That's like the highest pressure in the rocket engine. You can read the numbers. And you can see we have this fuel coming to here and coming to here. Then we have oxygen coming to here and here. These are called pre-burners. This is the fuel pre-burner. This is the oxidizer pre-burner. So what it does is basically it combusts. Now here's the fun part. Not all, most of the fuel is pumped into the pre-burners here and here. Only a very small part was pumped to here. You saw that. Here in the oxidizer side, most of the oxidizer was directly pumped into the combustion chamber. Only a small part was pumped into pre-burners. You remember about the mixture ratio. You have a lot of hydrogen, lot of fuel, and a very small amount of oxygen for the combustion. So now we have a fuel-rich combustion. You have a lot of hydrogen, a small portion of oxygen. So only a small portion of hydrogen would burn, like it's relative to how much oxygen you are getting. So the rest of the liquid hydrogen, it doesn't burn because you don't have enough oxygen, right? Because the other, most of the oxygen are here in the main combustion chamber. So, but because of the combustion, remaining hydrogen is converted to gas. So now you have hydrogen gas and the combustion byproduct here and here. And that hot gas is used to turn these turbines and here, which turns the high pressure oxidizer pump, oxidizer boost pump, and high pressure fuel pump. That's how you get these pumps to work from the gas from the pre-burners. And after that, hot gas from both pre-burners are injected to the main combustion chamber. So now you have a lot of unburned hydrogen gas and you have liquid oxygen from the pump, and you combust them together and you have the main stage combustion. Now you can see, so in the main combustion chamber, you are burning as close to the optimum stoichiometric ratio. So you have 6000 degrees of Fahrenheit. But in pre-burners, you burn in a fuel-rich ratio. So you only got around 1000 degrees of Fahrenheit. So I told you earlier, you get the high maximum temperature at the stoichiometric ratio. If you are doing a fuel-rich or oxidizer-rich burn, you're getting a much smaller combustion. So this is how the RS-25 rocket engine works. So most rocket engines works kind of similar way, like not in exact way. Most of rocket engines have pumps, turbines, and everything, but in different configuration. We call these cycles of rocket engine. We have gas generator cycle, we have stage combustion, and here we call fuel-rich stage combustion. Fuel-rich means you are burning fuel-rich in the pre-burner. Then we have the other variant. It is the oxidizer-rich combustion. That means you are burning oxidizer-rich ratio in the pre-burner. Then we have full flow stage combustion. That means you are burning most of the propellants here and here, both fuel and oxidizer. So it's full flow stage combustion. So there are multiple types of cycles. You can like read this from internet. It's like not that complicated. So this is fuel rich stage combustion. It's one of the most complicated rocket engine cycle. I think now you get the idea how everything here works. And we have some other components for autogenous pressurization and vibration management and everything. So these are that other lines, and that's how RS-24 rocket engine works. Okay. So this is from Atlas V rocket launch. So before moving into the other part of the lecture, if you guys have any questions, so anything like it's not clear, you guys can like drop that into the chat, I guess, because the next part is kind of different than what we talked until now. If you guys don't have questions, we can move on to the next section. That is the modern rocket innovations and future of space travel. So up until now, I talked about like general stuff about rockets, but now we have like few specific points to talk about. So in today's world, what is happening with rocket? So here, like I want you guys to like engage with me here. So in current day, so there are like a lot of stuff happening in the space industry, rocket innovations and everything. So one of the coolest thing, I guess, is the fully reusable rocket or fully reusable launch vehicle development. So currently we have two private companies working on fully reusable rockets. So one is obviously you guys know that is the SpaceX company, and we have a Starship. So this is from the latest flight, the 12th flight of the Starship. And this one is Stock Space. So this is another company in America, and they are building a rocket called Nova. So let's dive into both rockets. I think you guys know about Starship anyway, but I will talk about it anyways. So Starship, so Starship is basically the largest rocket humans have ever built, and it is basically 120 meters in height and 9 meters in diameter. It's made out of stainless steel, not aluminium. The key difference is this two-stage rocket is designed in a way that both stages can be reused. So that means you are not only land in the first stage, but also you are land in the second stage. We all have seen first stage landings. We have Falcon 9, Falcon Heavy, New Glenn, and over the China we have ZQ-3, Tianglong 3, which is not yet successful, but also Long March 12A. So there are a lot of rockets that have the capability to land the first stage. But land in the second stage is much more challenging because second stage is the one that carry the payload to its intended target or the orbit. So that means if you are in the low Earth orbit, the second stage is traveling at the orbital velocity. First stage is like usually separated at much lower velocity, like 8,000 kilometers per hour, 10,000 kilometers per hour. It's relatively slow. So it is relatively easier for it to land. But the second stage, it's going at orbit velocities, which is like 28,000 kilometers hours or higher. So when you are coming to Earth at that speed, there's a lot of heat generated at the atmospheric entry. So you have to have heat shield and everything as a spacecraft coming down to the landing. So in Starship, it only has fuel to reach the low Earth orbit. But the Starship is designed to go to Mars. In order to do that, it has to be refueled in orbit. So this is orbital refueling. So you have one Starship carrying the propellant and the other Starship has humans or cargo or anything. So the tanker Starship refills the human or cargo Starship in orbit. After the refilling, the Starship can reignite its rocket engines and go to Moon, Mars, or wherever it's going. So without orbital refueling, Starship is stuck to low Earth orbit as the space shuttle. So as I said earlier, if you have any questions, you can just drop it in the chat. So currently Starship is under development. So that means SpaceX is testing the Starship. So right now they have their third variation. So they call the third generation or V3. So they had the first launch of the Starship V3 back in May 24th or 25th. I don't remember, like it's in the last week of the May. So it's just a few weeks ago. So flight was mostly successful. The first stage was able to push the second stage into its intended orbit, but the boost back burn and landing failed for the first stage. Second stage also had engine failure, but regardless of that, it was able to land. So that is a good thing. So the ultimate goal of SpaceX is to send Starship to Mars and build a colony on Mars. So it is in distant future, I guess. Right now, Starship is still in testing phase. So city on Mars, that's a good dream for this century, I guess. Now we have the other company, Stock Space. So it also has a reusable rocket, but it's different. So this is a smaller rocket. It is not as big as Starship, but it's a full reusable one anyway. So this is the second stage. Okay, we have a question, but I will explain this after this segment. Okay. So this is the second stage of this NOAA rocket. This is actually like a kind of a hop. So very short flight of that second stage. One of the things you need to note is you cannot see a clear rocket exhaust here. So this is not the rocket exhaust. You can see kind of a flame, but you can see it's not like a rocket engine exhaust. It's kind of a flame, not a rocket exhaust. If you can see, the rocket engines are at this circumference, like there are like multiple rocket engines around the circumference. It's not very visible here. But in this animation, you can see that. So after the first stage separation, they are, oh, sorry, rocket engines are basically around the circumference of the here. And the center part is the heat shield. On the Starship, the heat shield is on the side of the Starship. But on the Nova rocket, second stage, the heat shield is at the bottom of the second stage. So that's a key difference. So this one also needs orbital refueling. So one second stage can refuel the other second stage. So it will allow the second stage to go to the higher orbits or even to moon. So yeah, so they are also aiming for the Mars. Sorry, moon. I'm sorry, moon. So this is also they can use this reusable second stage to capture like dead satellites, orbital debris, and then here's the cool part. It just re-enter the atmosphere like a space capsule and reignite the rocket engines for landing. So that's their target. Currently, they have tested their second stage like this. If you remember, SpaceX also tested their second stage first back in like 2020, 21. Now they have the full rocket. So stock space is like few years behind SpaceX, but they will get there, I guess. So these companies are developing full reusable rocket engines as of today. And China is also developing a reusable rocket, but China is not very open about their rockets development. So they are developing a rocket called Long March 9, which is similar to the Starship. It might be bigger than Starship. Let's see in the future. But they are developing a fully reusable rocket. So next, we have advanced rocket engines. So now I will explain the question we have. How is the optimum mixture ratio selected for different propellant combination? Okay. The best mixture ratio is the stoichiometric ratio. So that is when you mix the exact fuel and oxidizer amount to get the combustion of all the fuel. So the leftover would be just combustion byproduct. If you burn hydrogen and oxygen at the stoichiometric ratio, you will get water vapor. That's it. There's no hydrogen or oxygen remaining. So that is the best. But since you have some practical limitation, if you need a cooler temperature in the combustion chamber, you could shift the ratio towards the fuel rich or the oxidizer rich. Then again, we have a practical issue. If your engine is running fuel rich, that means you have leftover fuel. But if you are running oxidizer rich, you have leftover oxygen. Now, what's the difference? Oxygen now, like it's at very high temperature and it's oxygen. So what does hot oxygen gas do? It will try to combust something because you don't have enough fuel. There are remaining oxygen, and these oxygen atoms, basically molecules, will start to burn the inside of the rocket engine. So that's what happens. If you have leftover oxygen in the combustion, it will try to combust the inside walls of the rocket engine. Most rocket engines are made out of copper alloys. So copper will ignite with the oxygen. So you can have advanced material alloys which are like resistant to high temperature oxygen. But the easier way is to run fuel rich instead of oxidizer rich. There are some oxidizer rich rocket engines. They have developed their own alloys that can withstand high temperature oxygen gas. So there's that. And why is methane like becoming the popular choice for reusable rockets? Okay, that's a good question. Like historically, there are some people in the history, like even in 1930s, who has like developed methane fuel rocket engines. But like in modern days, Raptor, the SpaceX Raptor engine is the first one use methane as the propellant. So the reason is basically it is sit in like kind of a sweet spot between the kerosene and liquid hydrogen. Okay, so the liquid hydrogen has the highest efficiency, the highest specific impulse, but hydrogen has a much lower boiling point. So it is around 253 minus 253 degrees of Celsius. So that is 20 Kelvin. So it is very cold. And hydrogen has a much lower density. So it needs to have big tanks, which add to the weight of the rocket. And also handling liquid oxygen is kind of a nightmare. It can leak from even a small crack. So it's kind of dangerous. So in the other side, we have kerosene or the RP1. So this refined kerosene, it's a liquid at room temperature. So it's good. We don't need cryogenic insulations. But these hydrocarbons burn. This hydrocarbon doesn't burn in a clean way. It has a lot of leftover carbon, which builds up in the inside of rocket engine. So it's called caulking of a rocket engine. So if you burn kerosene, you have a lot of black carbon particles remaining in the rocket engine. So if you are making a reusable rocket engines, that is not good because you have a lot of carbon build up in the rocket engine. You need to clean it after every flight, like Merlin engines does. So if you are doing like a kind of a rapid reusable rocket, that's what SpaceX is trying to achieve with Starship. It just land, refuel, launch again. So you don't have time to clean, build it like carbon builds and other things. So in that way, methane is kind like it sit between both this kerosene and liquid hydrogen. That's why most modern reusable rockets tend to have liquid methane as the propellant. So back to the engine development. So this is the old Raptor, like from 2019, 20, I guess. So it's very complex. Then comes the Raptor 2 around 2022, 2023, I think. It's less complicated. And now we have Raptor 3. It is seemingly very less complicated, right? But the actual thing is, this is the most complex Raptor engine out of all three. Because most of these external plumbings, pipes, wires, and everything is now integrated into the rocket engine. So, like some parts have been removed, that's true, but like you cannot remove all the parts. So, like if you think, okay, all of these pumps and everything has been removed from the Raptor 3, no. Most of these items are like integrated into the rocket engine itself. So that's why you don't have external pipes, external wires, external sensors, everything. It's integrated. So this is actually like very complex rocket engine, because these external items are right now inside these walls. Like it's much more complicated compared to this. So from the outside it looks clean, but that means you have everything integrated into the rocket engine. So it's much complex to design and manufacture compared to this Christmas tree, as they called it. But it is not all. Like SpaceX is not the only company doing advanced rocket engines these days. Stock Space also have developed a full flow stage combustion liquid methane rocket engine. They called it Zenith. This will be used on the first stage of the Nova rocket. Then this is the second stage of the Nova rocket. This is the Andromeda rocket engine. So this is not like 30 rocket engines. Okay, like we think, okay, this 1, 2, 3, 4, 5. So we have 30 nozzles and combustion chambers, but all these like combustion chambers are linked up to a single turbo pump. So this whole structure is basically a single rocket engine with 30 combustion chambers. So that is the Andromeda rocket engine. Then from China, land space company, they have BF-20. It is also a full flow stage combustion rocket engine, burns liquid methane and liquid oxygen. It is similar to Raptor. Then we have Archimedes rocket engine from Rocket Lab company. It is also running on methane, you can say that. But this one is oxidizer rich stage combustion, not a fully flow stage combustion. And we have BE4 rocket engine from Blue Origin. It's also oxidizer rich stage combustion rocket engine, which burns liquid methane and liquid oxygen. Then we have BE7 engine. So this is going to be like kind of a new rocket engine. This burns hydrogen and oxygen, but in a completely different rocket engine cycle, which called dual expander cycle. I didn't explain the expander cycle, but it takes like a lot of time. But I think if you are interested, you can learn about these expander cycles from Wikipedia or internet. Okay, so this is like the new age of the rocket space industry. That is, as we all know, satellite-based high-speed internet and AI computing. So usually, internet was used to spread through world using fiber optics and cellular towers. But now we have a very special space component. So that is a satellite-based internet. So I think we all know about Starlink. So Starlink is SpaceX's high-speed internet satellite service. So this is the Starlink terminal or Starlink antenna. You need to attach it on a place where it can clearly see the sky. So how it works? It's simple. So you have the Starlink antenna on your rooftop. It will connect to the Starlink satellite. And these satellites are also interconnected using laser link. So that means each of these satellites have 4 laser links. That means 4 laser beams pointed at another 4 satellites. So all these satellites are moving in space. So one satellite has to track four of its like neighboring satellite, and vice versa. All these satellite has to track their neighboring satellite. So all of these satellites are interconnected through laser links. Then we have ground station operated by SpaceX. So this is where like the gateway to the internet. So ultimately satellites are connected to this gateways. So that's how you get the internet. So basically internet is connected to the Starlink gateway, and it's connected to the satellite, and satellites are connected to your antenna. So through a Wi-Fi router, you can get access in your home through satellites. So that's how basically the broadband satellite networks work. Then we have a very new satellite internet service. It is called mobile internet through satellites, or direct to cell. In acronym we call D2C, direct to cell. That means Starlink satellites can work as a 4G tower. Like we know 4G cellular towers, like we can see all around our country. So, but these Starlink satellites also can work as a 4G tower. So that means you don't need to have a Starlink antenna, but you can just directly connect with the Starlink as a 4G tower. So this is your 4G tower in space. So that's like 500 kilometers up, but it has a very powerful antenna. So it will send 4G signal to your mobile phone, and it will catch the weak 4G signal going out into space. Yes, like our mobile phones can send 4G signals into space, but it's very weak. You need to have very powerful antennas up there to catch that signal and make it work. So right now SpaceX have these small number of direct to cell satellites, but they are going to increase its kind of number of those D2C Starlink. So that's going to be the future. Basically, in the future, your mobile phone can connect to a satellite. That's it. You don't need mobile towers, like you don't need nothing. Your towers are in space. So right now there's like a global search for high-speed internet satellite constellation. So we, like, most of the time we hear about like Starlink, but it's just one of them. So Starlink, the owner of the Starlink is SpaceX from America. The target number of satellite at the end of the deployment is 42,000. Currently, they have launched more than 10,000, but the target is 42,000. So at one point in the future, we would have 42,000, maybe higher, maybe slightly lower, but around 40,000 Starlink satellite in orbit. Then we have OneWeb from Eutelsat in Europe. So they have a much smaller constellation with 652 satellites. Four of them are like spare satellite because they only need 648 for the operation. So it's basically completed internet constellation. Like they want to increase their number of satellite in their next generation, but currently the first generation of the constellation is completed. So they are basically providing services to business, not to end users, only to business. So that's why maybe you haven't heard about it, but the company is making profit last time I checked. Then we have Leo constellation from Amazon company from America. So they are targeting for 3,236 satellite. Currently they have 240 plus satellites deployed. Then in China we have Guowang. So this is a Chinese national satellite network. So their target is basically 13,000. Right now they have around 200 satellites deployed, but they are sending those satellite like in a high cadence right now. Then they have a future version called CTC1 and CTC2. They are going to launch 200,000 satellites. That's a big number. Like that's like 5 times the Starlink. Then, so that is Chinese central government. Then we have Shanghai local government. So they are trying to send another separate broadband satellite network called Qianfan. So they are targeting 14,000. Currently, they have launched around 162. And also from China, from a private company called Land Space, they need like Honghu 3. They are targeting 10,000 satellites, but they haven't launched any of them. Then Blue Origin company, they are targeting another 5,400. So it is called TerraWave. So this is kind of a different kind of service, because I told you SpaceX Starlink satellites have laser interconnections between satellite, but from the satellite to the ground, they are using radio waves. In TerraWave, they are exclusively providing internet service for businesses, not for end users. But they are providing not only radio connections, but they are providing laser links to the ground. So that is kind of like a complex thing, because you can have laser link in space because there's no atmosphere. But if you are sending a laser wave from a satellite to the laser beam from a satellite to the ground, you have atmospheric issues, but that's their target. Using laser, you can you can have much higher speed compared to a radio link. So that's TerraWave. I think they are targeting to launch 2028, I guess. Let's see. Then we have Iris 2 from Europe, from European Union. They haven't launched any of the satellite, and I don't know the number of target satellite. Then Russia, they have Sfera or something. I don't know how to pronounce that correctly. It's from Bureau 1440. So their target is 600. Okay, these numbers are swapped. So their target is 640 satellite. Currently, they have deployed 22 into orbit. Then from Canada, the Telesat company is targeting 198 satellites in a constellation called Lightspeed. So collectively, we have like 300,000 satellite in the future, providing internet for us, I guess. I guess that's a good thing, because these satellite internet connections are good in like remote places, in a jungle, on a mountain, in a desert, in the middle of the ocean, or in the sky, Antarctic, Arctic, anywhere you can get internet through satellites. But it doesn't stop there. The next chapter of the space industry is AI computing satellite constellation. That means you are sending data centers into the space. So SpaceX AI is targeting 1 million satellites to send to multiple orbits around the Earth, acting as data centers in the future. 1 million. So that's like a crazy number. Then we have another company called Star Cloud in America. They are targeting 88,000 data center satellites. Then we have Blue Origin targeting 51,000 satellite called Sunrise. Then China, currently they have announced 2,800, but we all know how China works. They will surprise us with 1,500,000 or something, like very large number of orbital data centers. So this is the new frontier of the space industry. Like SpaceX announced that they are sending like million satellites a few months ago. So this is like a very brand new thing. For example, so this is the initial design of SpaceX AI satellite. So this is Starship, 120 meters tall. This is the wingspan of the solar array is around 190 meters. So 200 meters. So that is very, very big. It has big radiators because it needs to eject a lot of heat from these computers, because essentially this is a satellite filled with computers doing AI data processing, training and inferencing. So there's a lot of heat generated from computers, and you need to eject this heat into the space. So that is why this is really good for a data center, because one of the key challenges of data centers on the ground is the amount of energy it needs and the cooling. So you need a lot of water, which is not a good thing because water is essential for everyone. So, but if you have a data center in space, you have sunlight, like infinite, not infinite, but you can get a lot of energy from sun. You need to have big solar arrays like this one. Then space is very, very cold. It is like 3 Kelvin. So very cold. So all you need is a large enough radiator to eject all these heat generated from computers. So that's all you need. So your energy problem is solved in space, and your heat problem is solved in space. So basically, this is a really good solution for data center issue on the ground. So that's why SpaceX is doing this crazy 1 million satellite orbital data center constellation. So, this design is from like few months ago, and today morning, like literally today morning, SpaceX released a completely different design for their satellite. Now the wingspan is not 190 meters; it's now 70 meters. But the width has width it the width it is increased. So this is the new design, and you can see radiators here and here. Now you have two radiators. So this is compared to the Starlink V3 satellite. So these are not in space yet. So these are for launching using starships. So this is the Falcon 9 version of the Starlink. So it's Starlink V2 Mini. So currently, Falcon 9 rockets are used to launch these kind of satellites to orbit. This is like 1.5 tons each. So this is Starlink V3. It will be used. It will be launched using Starship. So it is like, I think, two tons per satellite, I guess. So then they will move on to launching AI satellites using Starship. So 1 million of these and future versions of this AI satellite will be orbiting the Earth. And that's only from SpaceX. We have other competitors too. So, more technical details. So these satellites have average 120 kilowatts computation power. So that means these solar panels has to take 120 kilowatts of energy from sun and convert it to electricity. So that is the power used on computers. And these radiators has to eject all of that energy as heat back into the space. So that what happens. So you take energy from sun, use in computers, and the energy converts into heat, and you eject it. So the most challenging thing is the radiators. So let's see how they are going to do that in the near future. So anyway, SpaceX is pivoting into this new area in the space industry. So 1 million satellites in space. So this is not everything. This is, I think, 600,000 satellites in SpaceX constellation. So we need another 400,000 to be added into here. So it's going to be like large number of satellites. So it's going to be very challenging to keep these satellites from hitting each other. For example, these images are from Starlink satellites. So these are basically other satellites or some debris flying very close to the Starlink satellite. So here it is one thing, and this is also another thing. So SpaceX have reported these some satellite debris have come close to Starlink satellite, like in a range of tens of meters, like that's very close. and they are traveling at orbital velocity, like thousands of kilometers per hour per second, and you are passing each other at like 10, 20, 30 meters. So that is with 10,000 Starlink satellite. Now imagine we have 1 million SpaceX satellites and 42,000 another Starlink satellites, 200,000 satellites from China. Then we have all these other Star Cloud, TerraWave, and all these other satellites, maybe like 1.5 million, maybe 2 million satellites in space. It's going to be like a real traffic jam in space. So before we moving from AI thing, I just want to emphasize that AI industry is going to be the dominant industry in space in the future. For example, SpaceX is as usually taking the first step. So they are going to make the company as a public company, so from private to public. So before that, they have acquired XAI company, that is Elon Musk other company, where we have X, Grok, and other AI services. You know that, right? So XAI was acquired to SpaceX. That's the name. New name is SpaceXAI. So that's the name I used on the orbital data center name. So this was done in February, and few weeks ago, Google signed a deal with SpaceX AI to use their computing hardware, their data centers, and they are going to pay nearly $1 billion per month to SpaceX for using their data centers. And the Anthropic, Anthropic, right? They have Cloud AI. So Anthropic will pay 1.25 billion per month for using SpaceX data centers. So this is like now SpaceX is no longer a rocket launching company. They are now an AI services company, and the rocket launching is kind of a side business. It's like the revenue from the rockets are like very small portion compared to the revenue they are going to get from AI services. Okay, so that is the new frontier in space. So another AI company you might have heard, Cursor, they are soon to be acquired by SpaceX, maybe within like few weeks. I don't know. So I mean, we used to like treat SpaceX as a space company, but now it is a AI company. It's rocket launching, satellites, and everything. It's a side business. So that's the modern space age, I guess. Okay. So the last thing I want to talk about is the crewed lunar missions in the near future. So this beautiful image was taken by Artemis 2 astronaut in April when they are on the far side of the moon. You can see the Earth and the Artemis 3. So today is an exciting day because, okay, what's the time now? At around 9:30 p.m. today, I guess that is the time now, right? Okay, 9. Okay. I think in like 30 minutes or so, NASA will announce Artemis 3 crew, who are going to be flying on the Artemis 3 mission next year. So Artemis 3 is not going to the moon. It's a low Earth orbit mission. The goal is basically to test lunar landers in low Earth orbit. So in the Artemis program, we have 2 lunar landers. One is the Lunar Starship from SpaceX and the Blue Moon Mark II from Blue Origin. So both providers, SpaceX and Blue Origin, are required to launch their lunar landers into low Earth orbit next year, and Artemis 3 crew will rendezvous and dock with each lander in their Orion spacecraft. So this is not going to be a lunar mission, but this is a very crucial mission for the next Artemis 4 mission, where the humans will land on moon again after like 5 decades. So for the Artemis 4 mission, they will use the Lunar Starship as the lander. Artemis 5 also might use the Lunar Starship or Blue Moon Mark II, because now NASA is going with this 2 providers theory. They have two providers for ISS cargo. Then they have two providers for ISS crew missions, and now they have two providers for lunar landers. So having two, they can like minimize their risk and maintain like good competition between companies in America. So that's a good thing. So, but like Artemis 4, 5, 6, and there will be lunar landings on moon. But end goal of NASA is to basically build a lunar base on the moon. So it's kind of science fiction area right now. So NASA revealed about these plans few weeks ago. So they expect a semi-permanent crew presence on the moon in a moon base by 2032. So that is like 6 years from now. It's a very short period of time. So first base is right now. So they are sending 3 spacecraft to the moon, which rovers and all the other kind of equipments to find out what is the best place to build a lunar base. And so like the area they are targeting is the South Pole, because South Pole of the moon has a lot of craters that have permanently shadowed place. So in there, there's vortice. So if you have vortice, you can get water, you can make rocket propellants, and you can sustain life to a certain level using water, right? So this is the like their moon-based phase 1 targets. CLIPS landers means commercial lunar payload services that American private companies are sending their lunar landers to moon as per NASA contacts. Viper is a rover, Moonfall drone. There are a lot of things going to happen in near future. So in this year, we have 3 American spacecraft slated to go to the moon. So the first one is Blue Origin's Blue Moon Mark 1 lunar lander. So the Mark 2 is the bigger one, which can carry humans. So this is a unmanned lander. So it's basically done now. They are testing it, but the bad thing is the rocket exploded. If you saw news like few weeks ago, Blue Origin's New Glenn rocket exploded. That rocket was going to be used for this launch, but now the launch pad is destroyed. Rocket, the accident investigation is underway. Sorry. So Blue Origin has to find a new rocket to send their already completed lunar lander to the moon. Then we have Robotic company sending their Griffin lander, and Intuitive Machines has their Nova C Trinity lander. So all 3 of these landers are slated to launch and land on moon in this year. So this is considered as the phase 1 of the moon base. Then we have lunar drone program. So that is basically you are sending small landers to the moon. Then from there, it just flies over a certain area, photographing, mapping what's down there. Because in order to find make a lunar base, you need to be certain that you have vortice nearby and some other things. So drones are basically used to characterize the land. So that's why these 5 kilometers range drones are sent to the moon. So currently the Firefly Aerospace got the first contract to build and launch 4 lunar drones in the coming years. But America is not the only country is trying to go to the moon right now. All these American efforts are like they always wanted to go back to the moon since President George W. Bush back in like early 2000s. But now China is also trying to send humans to the moon. Now the Americans are like doubling down their efforts to go back to the moon before China does. So China is trying to use a simple, more less complex way to send humans back to the moon. So America is basically trying to use Orion spacecraft with much more complex Starship and Blue Moon Mark II lander. But China is going with simple Apollo architecture. So you have a mothership called the Mengzhou. Then you have the lunar lander. So it's called Lahiru. So they are not building a Saturn V class big rocket. Instead of they are building two Falcon Heavy class rocket called Long March 10, which is much easier. So they use two rockets to launch Mengzhou and Lahiru to the moon, and in lunar orbit they dock. The crew transfer to the lander. They land on the moon, come back to the lunar orbit, dock with the Mengzhou. Crew go back to the main spacecraft, and they come back to the Earth. So this is like the Apollo missions. Only difference is both the lander and the mothership was launched on a single rocket, which was a much bigger super heavy class Saturn V. So China is taking a shortcut, launching two spacecraft on two smaller rockets. So this is not just some plans they have. They have already tested their Long March 10 prototype with the Mengzhou spacecraft on top. Also, they tried to land the first stage of this rocket onto the onto the ocean, but this ship in the background. So next time they are trying to land this booster into the ship. So this basically, you remember the Starship first stage is like it is being the two big Mechacilla robo arms are used to catch the first stage. Here they are using kind of a cable technique to catch the first stage in the ship. So the ship will land into the ship, and there are some cables. It will just grab the first stage instead of a hand, like in a Starship. So they are trying to use reusable rockets to send classic capsule and a classic lunar lander to moon. So their method is kind of a simple and more, how do you say it? Their timeline is much short. So they started building these rockets like few years ago, but they are now testing it. In this year, they will launch the full Long March 10 rocket. So that was a prototype, a small version. This is the full one. So it's already on the launch pad. They have like full-in test. They have conducted full-in test. The first launch will be, I think it will happen in few months. So China is targeting 2032 land their first group of astronaut on the moon. NASA is targeting 2028. So next year they have Artemis 3 low Earth orbit mission. In 2028 they will have Artemis 4, the lunar landing. So they are targeting 2028. China is targeting 2030. This is only 2-year gap. If China can work a little bit faster, or American program, if it got delayed a bit, we might see a real moon race. I don't know. Let's see. Okay, so thank you everyone. That's all I have for today. I think you learned something out of this webinar. Again, I want to thank SEDS SLTC for inviting me, having me for this session today. So thank you very much. So back to you.
Thank you so much, Mr. Lahiru Udara, for that fantastic and insightful presentation. I'm sure our audience has learned a great deal from your session today. Now it's time for the Q&A session. If you have any question, you can scan the QR code displayed on the screen or simply drop your question in the Zoom chat box. We will try to answer as many questions as possible. A quick reminder, if you have any questions, please drop your question on the Zoom chat box. We will answer as soon as possible. Thank you.
Okay, we have two questions. The first one is what happens if the pressure drops below the required value during flight? So most of the time, that's the end of the rocket engines, because here's what happens. So you have the pump in the inlet of the rocket engine. So from the tank, all the fuel or the oxidizer, the liquid comes to the pump, then the pressure increases and sent to the rest of the engine. Now imagine the pressure drops in the inlet because the tank pressure drops. What happens is, as the pressure drops, the flow of the liquid also drops. So in that case, the pump doesn't have less resistant from the, it has less propellant to push. So the speed of the pump increase, and if it increase above a certain value, the pump just explode due to the centrifugal force, because it can handle only up to a certain speed, and after that the pump just disintegrate and the pump will explode. So also before that, the tank structure might fail if the pressure drop below a certain point. So it could go either way. The rocket might just crumble at a certain point in the tank and it will just explode, or the pump will explode due to the over rotation caused by the reduced flow rate. So either of those scenarios can happen. How does the Andromeda engine balance performance with reliability? Okay, the one thing is basically this is not the first time like people are trying to attach multiple combustion chambers to single turbo pump. So for example, Soyuz rocket have 8 combustion chambers in a single pump. So this rocket engine has 8 nozzles and 8 combustion chambers. So it's a very reliable rocket engine, RD107 and RD108. And RD170 also had 4 combustion chamber. It's still the most powerful liquid propellant rocket engine in the world, RD170. So having multiple combustion chambers doesn't affect the reliability like that way. But yeah, it's more complex than a single thrust chamber and single nozzle. So they have to make sure everything is working perfectly. Of course, the first flight might fail, but let's see. The reason they are doing this is they need to have that big heat shield in the middle, and you cannot have a rocket engine nozzle at the center because it will just open the heat shield. So that's why they are using that circumference, the outage of the heat shield to attach each nozzles. So that's the reason they are going with that design. But let's see. I mean, that's kind of a new rocket engine design, so it's going to take some time before it becomes reliable enough, I guess. How will Artemis 4 contribute to the construction and operation of Luna Gateway? Okay, Luna Gateway is basically dead. So on the revised plan of NASA, Luna Gateway is no longer in their plans. So it's basically dead. They are going to repurpose a module from Luna Gateway as a nuclear rocket engine test bed for NASA. So the first module, called the Power and Propulsion Element, PPE, the first module of the Luna Gateway will now be named Space Reactor 1, and it will be equipped with a nuclear rocket engine, nuclear thermal rocket engine. So NTP, nuclear thermal propulsion. So that a new spacecraft will go to Mars. So, but that's not going to happen like within like few years, I guess. I'm not sure, but I don't think it's going to happen that fast. But that's the current plan of NASA. Please remember that NASA is a government agency and their plan change with the government. So every 4 years, there's a presidential election. Sometimes the current president wins and serve for 8 years. Sometimes a new president comes in. So when that happens, the NASA administrator gets swapped and sometimes some plans are revised. So this is kind of like that. Luna Gateway is dead. So Artemis missions doesn't have anything to do with Luna Gateway now. They will just go there and land, and there will be moon base in the future, but no Luna space station around the moon. I mean, if you really want a space station around the moon, you can just use a Starship, because a Starship is a really big spacecraft. The internal volume is, compared to the International Space Station, is around 1000 cubic meters. So all these module in the International Space Station has a combined volume of 1000 cubic meters, and a single Starship has around that kind of volume in the living space. So all you need is a single Starship as a space station. So there's your new Luna Gateway, I guess. So I guess those are all the problems. So thank you for the questions. I hope you guys got answers. So
Thank you.
oh,
Those were some fantastic questions. Thank you everyone for your active participations. And special thank you Mr. Lahiru Udara for answering them clearly. Before we move to the closing remarks, we would like to present a special token of appreciation to Mr. Lahiru Udara. On behalf of the entire organizing committee, please accept this virtual trophy as a symbol of our sincere gratitude for your valuable time, knowledge, and support in making today's session a great success.
thank you very much for this token of appreciation. Again, thanks for having
As we
me.
officially wrap up the third session of Space Tech webinar series, now I would like to invite our technical team head, Sinit Senaratne, to deliver the vote of thanks.
Thank you, Tardu. Good evening, everyone. As we conclude today's sessions of the Space Tech 2026 webinar series, session 3, the foundations of rocketry and the future of Space Travel, organized by the Satellite and IT Division of SEDS SLTC. I would like to extend our sincere gratitude to everyone who contributed to making this session a success. First and foremost, a heartfelt thank you to Mr. Lahiru Udara for joining us as our guest speaker and for delivering such an informative and inspiring session. Your insights into the principles of rocket flight, rocket structures, propulsion systems, and modern innovations in rocketry provided our participants with a valuable knowledge and a deeper appreciation of space technology and its future. I would also like to thank all the participants, SETS members, and SLTC students for joining us today and for your active engagement throughout the session. Finally, as a member of the organizing team, I would like to appreciate the dedication and hard work of everyone behind the scenes, whose efforts help make this session a success. Once again, thank you, Mr. Lahiru Udara, and thank you to everyone who joined us today. We look forward to seeing you in the upcoming sessions of the Space Tech 2026 webinar series. Have a wonderful evening ahead. Thank you.
Thank you, Sinead. Before we end off today's session, we would like to take a group photo with all of you. We kindly invite everyone to turn on your cameras and join us for the group photo. Please smile and look at this camera. Thank you for being with us today. Let's capture the beautiful photo. 3, 2, 1, smile. Thank you, everyone. And thank you once again, our wonderful audience, for joining us today. This is officially concludes the third session of Space Tech webinar series. We hope you enjoyed today's session and gained valuable insights. Signing off as your moderator, I'm Tharindu Pehasara from SLTC Media Unit. Thank you. Have a nice day.